I would like to welcome you all today to our EasyPower webinar on advanced arc flash hazard options. This is the second version, and the topics that will be discussed today are regarding arc flash in the dynamic stability module and arc flash in the short circuit option with in the integrated calculation method within the arc flash in the short circuit module. We'll also compare the integrated calculation method results with the momentary calculation method results and show you how those are different and where you may look at using one method over the other. So, and then we'll wrap it up with some questions if you have any. So to begin with, we're going to discuss the arc flash hazard calculations within the dynamic stability focus. The nature of this session today is not to go into the details of stability, but to give you an overview if you know how to use stability and understand it, how to get the results and what those results mean. So if you haven't been used dynamic stability, there are some other video sessions that are on the website from this webinar series that discuss stability that you can go check out. But the overall nature of dynamic stability is it's a system that's been around for a number of years, and it's basically a time response of typically no smaller than a half a cycle as far as how the analysis works. It's not for fast transients. There are other applications for that. It's a time response simulation of machines and control systems. It's basically taking a solution at the next time step based on the previous time step, and so each time step the system gets updated. So as far as arc flash goes within the stability focus, you don't have to have dynamics data entered to be able to run arc flash within the focus, but it will change your results if you do. It will give you a better representation of your system. Within stability, the system uses either a single bus fault to run the calculation for the arcing fault. You can't do a fault all as you can in the short circuit. It would be on a case-by-case basis, and the stability focus will simulate the protective device tripping and update the system as devices open and equipment is removed from the system. That's part of the updating the system. Looking at the protective device behavior as far as within the stability focus, fuses, low voltage breakers, overcurrent relays, under frequency relay, contactors, ATSs, over voltage, under voltage, and source inverters, solid state blocking action. These are different protective device applications that are available within the stability focus, and they will all be looked at, and they will modify your system if you have an under frequency case, or for a contactor, if the voltage drops too low, that will trip whatever is out below that, and then you'll see the response of the system as those conditions change. With arc flash, the three that we're most concerned with are the overcurrent devices, and those include fuses, low voltage breakers, and relays. It's the same as if you're doing a standard arc flash hazard analysis within the short circuit. We're looking at those same devices as far as how long it takes for it to trip, when will it trip off, how will relays still look at breakers and add an opening time for the high voltage or medium voltage breaker. So there's a lot of similarities. It's just that the way we determine whether the device trips or not is slightly different, and how long it takes. So when it comes to determining when a device will trip, the software within the stability focus does a simulation in a set time step. It's much quicker typically than a half cycle. But for determining a trip device and how long it takes to trip, we don't, the amount of time that the simulation would take would be much longer if we did it every time there was that we actually looked at the system. So in the devices, we evaluate them at every half cycle. We still use the TCC curves for fuses and low voltage breakers. We use the maximum clearing time as you would in the short circuit engine. Same thing. If the current that it sees hits on the TCC curve, then the time is evaluated at that current time step. But it's only for that time step, so we're accumulating it over a period of time. Once the device meets a certain criteria for it to trip, then the device that's associated with it is opened. So if it's a fuse, the fuse switch part will open, or the low voltage breaker will open. If it's a relay, then it will send a signal or work with the breaker and know that it needs to do that time. That time that the breaker takes to open will need to be added on to this other time, and for it to open. So how do we, since we're looking at it on a time step interval, how do we come up with when the device is going to trip? Because in the short circuit, if you're using the momentary method, basically we look at the momentary current, view where it sits on the TCC curve, say it's 10,000 amps of fault current. If you look at the TCC curve, it says it trips in 0.25 seconds. Then we use 0.25 seconds to calculate the arc flash incident energy. However, we're only looking at it for a short amount of time, in this case a half cycle. So so we're going to accumulate something over time, and once it gets to a certain point, then it will trip. For fuses, the I²T is used, and once that is met, then it will trip. So an I²T is calculated for each successive check, and then if that number is greater than or equal to the I²T at the point that it's tripping, then, or at that individual point that we're simulating, then that device is tripped. If along the way, once the device has picked up, the current drops down so it is no longer accumulating, this last line says that for this fuse, we do not dissipate any of that accumulation of energy, and we continue from that point if the current would rise and the device would pick up again on the TCC curve. For low voltage breakers, we do something slightly different. It's the same with relays. In those cases, we accumulate the time. So if a device picks up, we have, if it's a half cycle, it takes that half cycle and then accumulates all those half cycles, looks at the particular current, looks at the current, and if on the TCC curve, if that time that's been accumulated is higher than what it is on the TCC curve, then that device will trip at that moment. As far as the last statement, which if current drops below the pickup, the device will perform an instantaneous reset. So this is slightly different than the fuse. So if it's accumulating and the pickup drops below and is not seen on the TCC curve, then there's an instantaneous reset. As far as if it picks up again, it'll start from 0 and accumulate again. For overcurrent relays, we also use the travel time to determine when the device will trip. And again, it accumulates over the time steps. Similarly to the low voltage breaker, if the actual time is greater than the time evaluated on the trip curve at the current interval, the device will trip. But with the relay, once the device trips, you still have potential for breaker delay or some tripping device or clearing device, and then you may also have some other auxiliary delay. So those numbers are all taken into account after the device trips, before the device is opened on the one line and the system is reconfigured. For the overcurrent relay, the method that's currently used for the travel back, as far as if the pickup is reduced, follows an induction disk travel back time, and there is a procedure that's used. So it does take some time. It's not an instantaneous return, and it will. So if it picks up again, it'll start from at whatever point it's traveled back. So it follows an induction disk travel back. So in the stability focus, in the options, there's an arc flash section, and you can do a few things there as far as set that you normally see within the arc flash, or within the short circuit focus for arc flash. Arcing current, we only look at one at a time. For low voltage, you would need to look at both. Working distance, you can either set it there, or you can enter 0 and it will follow what's in the short circuit focus options, and you can also set the maximum time. For arc flash simulation for faults, the checkbox needs to be checked. By default, it's not. It is not checked. And within stability, only the IEEE 1584 equations are supported. There's a few other things that you should be aware of within the options. One is the simulation time step. This is not the number that, as far as when the devices are, the protected devices are looked at and where they're evaluated. It's hard-coded at a half a cycle. This is for the actual simulation of the DS or the stability simulation. That's one thing I wanted to draw your attention to. The others are the enable all protected devices, enable contactor action, enable ATS action. At the beginning, I mentioned some devices that would be included within this arc flash. You don't have to include them all, and those are set here. If you don't have enable all protected devices checked, then you will not be able to, the protected devices will not be looked at, and therefore your arc flash results will be misleading. But there may be an application where you don't want to see how long it trips. You just want to see if it takes a certain amount of time what that incident energy is. But there may, so most likely the enable all protected devices will be checked. The enable contactor action, enable ATS action, those are specific to stability. And when we talk about the integrated method, the contactor and ATS action are not supported within that method. So with that, we'll look at EasyPower and show you a couple examples of how this is done within the software. So for those of you that are familiar with the stability focus and have tried a demo or used the tutorial, this is the one line from the tutorial. It's DS example 2. I've made a few modifications, but overall this is that example. So the first thing I want to do is go into the stability focus. Up on the ribbon, I'm going to click the stability, and you'll notice that we have a few different windows. We have the one line, and then we have a plot window, and then a message window. When we do arc flash, we'll look at all of these windows. So for this example, I'm going to fault a couple different cases. One is with a radial system, so I'm going to fault switchgear 1 or switchgear 3, and this is one of I changed this name for this example. If you're looking at the example file, if you go back to look at that, and then we'll also look at switchgear 13.8, and that's because this is going to have multiple sources, one for the utility and one for the cogen, and see how that responds. So I'm going to go to the DS options and make sure that we got what we're looking for enabled. So all the protected devices are enabled, and then I'm going to go to the arc flash tab. We're going to use the 100% arcing current, working distance of 18, maximum time is 1,000, and this is checked, so we will see arc flash results. So just wanted to make sure that we were going to get what we are looking for. And so in the messages, everything has initialized. And I'm going to fault, and actually before we do that, I got to show you one more thing. When you do a bus fault, for this example, I've set the fault time length to 7 seconds, and our simulation in time will be 6 seconds. So for an arcing fault, we also need to make sure that this fault time is more than the actual simulation, so that your fault doesn't end prior to the full accumulation of energy. There may be a case where if you're actually doing stability, that you just want to look at a short fault, how your system responds to a couple cycle fault or maybe a second fault, and then see how it responds. So this is where it can be set. But for this case, I want to make sure that my fault time is longer than my simulation time. And for this case, it's already been set that way. So I'm going to double click on the switchgear 3 bus to fault the bus. And it's going to take a little bit of time here to run through this calculation. And so the results on the one line are power flow results at the end of the simulation. So you can see that during our simulation that the contactors for the motors dropped out. We also had breaker BHTX3 go from a closed position to an open position at some point during the simulation. And that looks like all of our changes. So a couple things to look at here. One is in the plot window, we show three useful pieces of information. You can show switchgear, or we have switchgear 3 voltage in per unit. We have switchgear 3 in amps, and we have the arc flash energy. So I'm going to go click on the plot, and I'm going to go to data cursor so that we can see what the results are as we move through the window. So the first thing to notice here is that, and I'm going to pull up the messages right after the initialization. So the first thing is the simulation ran for 1 second prior to our fault. So just after 1 second, we had a fault and initiated our arcing fault. The contactors here, right after that, picked up. Also, relay 1 and relay 6 picked up on overcurrent. That was all just initially right after the fault occurred. So relay 6 is this relay, and relay 1, I believe, is the generator relay. So as we continue through, and you can see this as we work through the window, that this first dip was a result of the fault, and then the second point where you see a sharp change is when the motors dropped out of the system. So, and that's because the contactors dropped out. Now, once the motors dropped out, relay 1 no longer was on the pickup part of the curve, or was not seeing a time on the TCC curve. So it began to travel back, and at a few cycles later, it had completed its travel back. Now, the simulation continued, and at 1.9 seconds, relay tripped on overcurrent. So relay 6, which is this relay, tripped on the overcurrent. Then it sent out a signal to that breaker, and the breaker opened. It found out how long it takes for that device to open, and so also looked at the auxiliary time, and then at 1.9916 seconds into the simulation, the breaker was opened. And so that's where you see the next drop-off. At that point, this green line is our accumulating arc flash energy. So at that point, here is when the device breaker opened. That shut everything off on that section of the system, removed the fault, and so the simulation continued, but there was no increase in the incident energy. At the bottom of the window, it gives you the information that you're looking for that fault. We had set it to 100% scale. It's at 35.6 calories per centimeter squared at 18 inches is our energy, and this is the amount of time and the boundary. So there's quite a bit of information, and there's as far as how the device tripped and why it tripped, and you can see that when you're using the momentary method within the short circuit engine for arc flash, that you're just running a straight current. It's the same for the whole simulation or the whole calculation. Where this method, you can see how the system changes and adjusts and see how that energy is accumulated for different things that happen within your system. So this is one of the main features of using arc flash within stability, especially if you're looking at things dropping off. You can also so the next point, or the next example that I want to show, is within the switchgear 13.8 bus. So the first case that we had was just a radial system. We expected this relay to trip for a fault at switchgear 3. Now, when we get into switchgear 13.8, and I'm going to fault this, it takes a little bit of time to run this calculation. We have multiple sources that are supplying power. Therefore, to shut off both device or both sources, multiple relays will need to be tripped. Their connecting breakers need to be opened, and then the source, the energy is accumulated. So you can see just off the bat here, since we're still down here, this is updated. We have in this case, 82.8 calories per centimeter squared at 18 inches is our result for this case. It took 4.3 seconds to clear, and the boundary is quite large. You can look at the curve again. We started after a second into the simulation, and there was a sharp drop right at the, or there was a drop in voltage and current right at the when the fault occurred, and then at a certain point it leveled out a little bit, and then at this point something else happened and it leveled out completely. And as time went on, you can see that the energy just kept accumulating until it was at 83 or 82.8 calories per centimeter squared. So let's go through the message log and see what all the software tells us it was doing. So again, we had the initialization stuff, and then at 1 second, the bus was faulted. So now we have a whole number of contactors that picked up. So we have contactors for all these motors, and they picked up right away because of the fault condition. So, but also at that time we had a number of other devices, relays that picked up. We had relay 10, relay 1, and then relay 5, I believe it's this one, and relay 7 is this one. So all those relays picked up. The ATS had an issue, even though we're really not concerned with that, but it lets you know that it had it picked up on undervoltage. And then shortly after the fault occurred, relays 5 and 7, the current was reduced and they were no longer accumulating time, so they began to travel back. And then after a short period, which 0.05 seconds, I believe, all the contactors for all the switch, all the 480 volt equipment, or 480 volt motors and 4160 motors all dropped out. Then a short time later, relay 1 and relay 10 are still accumulating time for tripping as we move through this simulation. So the first device to trip is relay 1, which is the generator relay. And adding on the breaker opening time, that breaker went out of the system at 1.76 seconds, which is about 76, or about 3/4 of a second into the simulation. The generator was offline. Now so that's at this point on the curve. That's why it goes to a straight line, because we have a utility, and the utility does not have stability information. It's not changing. It's a solid bus. And so now for the next, until we trip again, the utility is our only source in the system. So continuing on, ATS tripped on undervoltage. It's waiting to transfer, so it's going to go to its standby generator for this to supply this panel. R10, relay R10, at 5.24 seconds, it finally tripped. So basically, the amount of time through all the time steps finally hit that point on the curve, as we discussed earlier, and it opened the breaker, BH utility, which is this breaker, and at 5.32 seconds. So at that point right here, that's where our arc flash simulation or accumulation ended. So we have an arc flash energy of 82.8 calories per centimeter squared, and it took 4.3 seconds to clear that fault. So there's a number of things that you can use this for to give you more information as far as what's going on and how a fault affects your system. One thing I wanted to show you is if I go into control, and I'm going to take off the enable contactor action and enable ATS action and just use the protected devices. So I'm going to fault the switchgear bus again. And it's going to take a second here to run through the simulation. And it's getting closer. So now, if we look at the message log, now we just have a whole bunch of relays that picked up. All the contactors aren't there, and we have the relay 10. And so by leaving the motors in and letting the software determine how long it takes them before they're out of the system, or they died down due to the fault, it's slightly less. So the point of showing you this is that even though we left the contactors in and got rid of the motors, in short, it didn't really affect the arc flash incident energy that much. So you may want to see how, if you're running arc flash in stability, you may want to see how that affects your results. Also, another reason I want to show you this is that within the short circuit focus, we don't use the contactor, we don't use the ATS. Those are manual things within the short circuit focus. One note that I wanted just to mention briefly before we finish the stability discussion is stability looks, when you run an arcing fault, or you just run it in general, any device, any overcurrent device or protected device that has a curve, it's gonna include it. So in order to run this case, for this example, I removed the TCC for these two devices. So basically I was doing an excluding main that you would simulation similar to short circuit focus. If I wanted to include these devices, then I would have to go back in and set those. So so I'm going to go back to the database, edit focus here for a sec, maximize that, and then I got a couple slides here just to show you a few things, and then we'll go back in and discuss the integrated method within ArcFlash. The reason that I started with the stability focus, understanding that many of you may not have that, is when you use the integrated method, it's basically using the same fundamental elements of the stability focus. And the stability focus allows that to be shown a little bit easier because it's tough to use TCC curves to come up with numbers, and because the currents are changing and the time is being accumulated. So the main function of how we come up with, or how the software comes up with the incident energy, is an accumulation over time within this integrated method. The main difference between the short circuit focus and the dynamic stability focus is within the short circuit focus, the momentary interrupting and 30-cycle currents that you would get in short circuit are the ones that are used to determine what the incident energy is. But one of the main functions of the stability focus that is brought into the integrated method is if you do have a device trip and you still have other sources in the system gets reconfigured and recalculated, and the short circuit currents get updated to meet that the system configuration at that time. So if we go here, this is just a quick little visual as far as when you have multiple sources. So the case that we just had within the stability focus where we had the utility and the cogen. Under momentary method, what the software is doing is it comes up with a trip time, or I'm sorry, it comes up with a short circuit current at the bus that you're faulting, and then also the remote currents. It uses those remote currents to determine how long it takes each source to trip out. Then it looks at what the longest device is, and that becomes the trip time. So you may have a source that isn't in for very long, but that time is accumulated. So basically this picture shows that you're taking a time and a current, and you're basically getting this, you're accumulating the energy under this whole curve, where in the integrated method we are evaluating the current for the half cycle current for the first half cycle current, and then the 5-cycle current for the 5-cycle range, then the 30-cycle at the 30-cycle range, and then I'm at the end here I'm showing a system change, which may, like in our case we lost the generator, so there's less current because there's less source current. So now this would be where you only had the utility supplying it. So now you accumulate the energy over these smaller blocks, and your incident energy would be less. So this is the fundamental principle behind the integrated method, and why you may see different results, because we're looking at each individual time. Now, in the options under the calculate arc flash using, you need to set that to integrated. By default, it's set to momentary. I'm going to go back here. On these points right here, where we go from half cycle to 5-cycle and 5-cycle to 30-cycle, those can be set by the user. We've defined those as this point happens at 1 cycle, and this point here happens at 8 cycles. So by default, we use the half-cycle current from 0 to 1 cycle, then the 5-cycle current from 1 cycle to 8 cycles, and then beyond that we use the 30-cycle current. But at any point that the system may change, then we would change the system but continue to use that same current based on the new system. So this is just going to mention this. If you're, I would say most people just leaving it as the base default options is fine, but there may be a case where you want to see how something affects it. But this would be where you could update or change where those points happened. So there's 2 variables within the registry. It's under this folder, but I do caution if you're not used to being in the registry of your computer, you may get some additional help before you went and changed these variables. If you make a bad change in the EasyPower folder, you just have to reinstall EasyPower. But if you make it in the wrong folder somewhere else, it could have effects on your operating system. So do be careful if you're not familiar with that. But here are the three variables that we care about within the within the integrated method. These are them. These two are the ones that set the time. So here's our default, and here's the other default. And then the other one that people who are using integrated method, it's by default, we only show in the Arc Flash report, we only show one line. We just show the worst case. But there are conditions when you're working with multiple sources or multiple devices are tripping off, and you want to see how that, where those are and at what time those happen as you're working through this, that you may want to show that information. And this is a way that we can show additional information within the report. So it's basically showing multiple rows, and it occurs at each time a device trips. I do have one additional thing on that is if you are printing EasyPower labels from that, do check your result, or do check your label before you print out to make sure that the result is accurate, because that's you want to make sure, because we have the separate rows, that you're getting the row that you want. That's why it's not a default setting. So we'll come back and talk about this in just a second. We'll go back to the one line. So if I go into short circuit focus, go to short circuit options, I've got this set to excluding main. Times don't matter. And then the integrated, I'm going to set that integrated method and say OK. And let's fault. First, we're going to fault switchgear 3. And you can see, try to bring it all into the screen. So, in this case, relay 6, which is this relay, is the device that trips. You'll notice that we still, for the integrated method, we're still calculating both the 85% and the 100% in this case. So the pink shows that it's the 85% current. Now, the numbers that are shown in the one line, or I'm sorry, in the report, as far as bolted fault current and branch currents, are the current at which the device tripped. So if your device trips in the momentary range, then it will be the currents that are shown are momentary. If it trips in the 30-cycle range, then the currents that are shown are 30-cycle currents. That is a bit confusing, but that's that was the solution that we came up with for how to identify the different currents. So in this case, we only have one device tripping. It's the R6, and it takes 1.174 seconds, and to trip, add the opening time, and the arc time is 1.26. It's 37.7 seconds. So this case is a little bit higher than the number that we got in the stability focus for this same fault, which was 35.6. It also took a little bit longer for this device to trip, almost 0.3 of a second. So you will see, depending on the method that's used, you may see different results. Now, if we go go and perform the fault at switchgear 13.8, you'll notice now I have the option enabled. So this is what I was talking about, where we have multiple rows show up in the report. So relay R1, which is our generator relay, based on the stability, we would expect that relay R1 trip first. And it does at 0.679 seconds for a total arc time of 7.67. The incident energy at that point is 17.4 calories per centimeter squared. At this point, this breaker is now open. We don't show it on the one line, but the system behind the scenes is reconfigured, and now these currents here, or this source, is what's providing the fault current at that point. So if you look at our branch or our bus bolted fault current here, it's 7 or I guess this one, we'll start with this one, 8.99. That it matches this, but this one doesn't match because the system has changed. So if I was to, I'm gonna make one change here just slightly. So this number now, the 7.754, that matches what was in the other case. So that was the in condition. I'm going to close that breaker back in. So that 7.754 number, and so those are our numbers that are used to calculate, to come up with those numbers. So in this case, we started with the momentary current, then we went to the 5-cycle current, then we went to the 30-cycle current. Once we got into the 30-cycle current at 0.76 seconds, this device opened, the system reconfigured itself, and then continued until 4.32 seconds, 4.23, where this relay tripped, another 5 cycles for the opening time, and the whole system, there were no more sources at 4.32. So this number, 83.7, is your actual arc flash incident energy at that switchgear. So there's more detail in how this is or how we come up with the number than just saying here's our current, and based on your engineering experience, this seems to be like a reasonable case as far as how to come up with numbers for incident energy, because if you have a long fault that is a second or 2 seconds and you use a momentary current, that current is much higher than it would be the 30-cycle current is for that condition. So that is this case. One thing before we go, I want to show you how these numbers compare to momentary method. So if I fault this bus for the switchgear, you can see that it took 4.3 seconds with an incident energy of 118.3. And 5 seconds may be a long, or 4.2 seconds or 4.3 seconds may be a long time for this to trip. But you can see how we went from about 80 calories to almost 120 calories. That's almost 50% more. It's slightly less, but roughly 50% more than using the integrated method. So there are cases where you may see a more reasonable incident energy depending on which method you're using. But for a radial system, if we go back to switchgear 3, and because this time is much shorter, we went from 37.7 for the integrated method to 43 or 37.7 calories per centimeter squared for the integrated and 43.0 for the momentary method. So not a huge difference, but there is some difference there, and so I believe there are uses for these different methods. It's just understand what you're doing and be able to have an idea and be able to defend the instant energy that you have based on the method that you're using. So actually, wrong button there. I'm going to go back to the PowerPoint presentation, and just we have a few comments on the momentary versus the integrated method. Most people use the momentary. There are some people who do use the integrated method. For your typical analysis, the momentary method is faster, just as far as the amount of time it takes to do it. You can, one thing I didn't show is you can do a fault all with the integrated method, the same as you can do with the momentary method. It's just in the stability focus, you can only fault one bus at a time. But if you ran them side by side, typically the momentary method is faster because you don't have to run through all the simulations. For radial systems, the results are more similar. As we just showed, the 43 versus the 37, and that's a bit of a, that's a higher level. I didn't show any low voltage breakers, but if you have an incident, if you had no motors in your system and you just had instantaneous trips, the result that you get should be, if it's not the same, it's probably because of some the way that the integrated method is using the simulation and the step size. But they should be, if you don't have any remote currents or motors in your system, you should get pretty much the same answer. The longer the trip time, the larger the difference in the result that you'll see. That's because you're using, I should say this is a general thing, and it's generally that way because your momentary current is is higher than your 30 cycle current, which runs for a longer amount of time. And then the integrated method is most useful when evaluating loop systems or systems with multiple sources. So that's the area I think that you can see the best use, and if you can explain it, it's very valuable. So that will wrap up our discussion today. Just to wrap it up, we talked briefly about stability and arc flash instability and the way that the software goes through the simulation and how it evaluates the trip times and comes up with the instant energy. And we've also shown how basically that function from stability, how it's used within the integrated method to come up with a bit of a simpler view of arc flash, but uses a lot of the same methods as far as the calculation goes. And then in the end, just showed a little bit of why you may use momentary versus integrated versus stability. So I hope you've enjoyed and you've learned something from this webinar. I do have a few questions that were asked during the seminar, and if you want to stick around, I will try to answer those questions here. So let's see what we have. I had a question on current limiting effect of fuses. Are they considered in the DS method? No, they are not. They are basically, we're just looking at the curve if that's there and looking at the TCC plot. And then there was another question regarding why the 1,000 second was used for the max time for this discussion. The 1,000 second max time was used to show these cases. Some people do, drop that down to 2 seconds or 5 seconds based on, engineering judgments, or other methods. You may do. Basically, you're saying that if you drop it down, that whoever's working there won't be in that area at that time. The 1,000 second was just used today just so that the time would run completely and to be able to show that all these devices, what they needed to do to trip. I'll go back here to the switchgear. If I set for this device at 2 seconds, and I'm going to fault the switchgear. Actually, I need to fault the medium voltage one because the low voltage one tripped faster than that. So if I fault this bus, and I need to go to change this to integrated. So you can see that even though I showed the higher one, you could limit it to 2 seconds, and it stops at 2 seconds. It's slightly larger just because of the way the sampling is done. It always goes to the next sample before it gets in. It finds that it's over that 2 second limit. So, but yeah, you can set the 2 seconds. In this case, it would be 40.4 calories, and that option is available both in the stability function and in the integrated if so desired. But the intent was just today was to show that show how that worked. Okay, another question that we had was provide reason the mains to the medium voltage board are said not considered. Are you unlinking them to breakers, and what is the goal? Is it to see primary delay trip action only? In this case, I was just trying to simplify the example. There are cases where you may, depending on where you're working on this gear, that you may be able to include both of these mains. Maybe you can only include one. But the intention, as far as this goes back to the example that I was trying to show, that I wanted these devices to be the ones that were tripping. Basically, in stability, if I'm going to say no to that. So what I did was I just unchecked the plot TCC checkbox. So in stability, it bypassed it. If I put these back in, and they are, this one actually doesn't have a device because I pulled it out. So let's see. Say okay to that. Let's go find this. Okay, that's BH Gen feeder. Expand that a little bit. Okay. And we won't add an auxiliary time. And then let's go check this one. And that one does. So this one is BH main. So we'll scroll over here. High voltage fuse. BH main. Okay. So now if I go into stability and let me make sure everything's set up. Let's just leave that off for now. That's that. Okay. So if I fault this bus, or yeah, fault the bus, and we look at this, now it's 3.3 seconds because both of these devices, or I'm sorry, 3.3 calories per centimeter squared at 18 inches because these two devices are the ones that opened, and it was a much shorter trip. So depending on where you're at, you can do that. So I was just trying to show within, or I just mentioned that within stability that I wasn't looking for a result here. I was looking for the result here. And it's just, those kind of things are understanding your system and the system that you're evaluating to make sure that that you get the result that you're looking for and that it includes the information that you desire. One other question that came in is, what is the auxiliary time on the relay screen? The auxiliary time is if you have a second, you have a relay that's connected to a breaker, but maybe it has to go through a lockout relay or some other kind of device, and there's a delay that's not shown on the one line. So when if I go back, I'm going to go back to, let me go back to Database Edit Focus. So in the breaker, you have a opening time. In this case, it's 5 cycles. So if we're in the relay, this breaker will open in 5 cycles. But if you put in, say you had another relay that it had to go through or something, you could add that time in. So you could say 0.1 second is your auxiliary time. And I'm going to, just to show this, I'm going to do that. I opened this so the generator won't be a part of this calculation, and I need to set a couple things back. And I'm going to use the momentary method to show this because it works in all of them. I need to do including main. So if I fault this bus again. So you see this number is not the same as it was previously, and that's including the breaker opening time and the auxiliary time in that time, and that number is taken from here. So that's a little bit of what the auxiliary time is, and I think that's all the questions that we had. If you have any other questions, you can contact tech support and we can answer those for you. Thank you for attending, and look forward to hearing from you and having you a part of our other webinars in the future. Thanks.